Okay, so we ended yesterday with a discussion of some peculiarities of the decimal system. Just familiarizing you with the sorts of things that can happen for decimal expansions. But I mean, the main point of yesterday was that this fact that you might have long assumed was shown to be the case that any um, any rational number is exactly the sort of number that has an eventually periodic decimal expansion, right? That was kind of the main um, thing that we showed. So the last thing in chapter 11 that we're going to talk about is called the discrete log problem. The idea is basically this. Um, Suppose I want to solve. So if I want to solve, say, 2 to the x is equal to 140. Then the thing is that I can estimate what this x would be because I am using the fact that the function 2 to the x is increasing, right? And I know that I can estimate uh, this by saying, well, 2 to the 7 is 128, and 2 to the 8 is 256. And so it's got to be between, so x is between 7 and 8. And I know that it's probably closer to 7 just because 140 is closer to 128 than it is to 256. Of course, I can do this, again, I'm abusing the fact that 2 to the x is going in one way, right? It's increasing. Okay, and so this allows me to very easily come up with an estimate of what x is. So solving something like this is pretty easy because of that. So the idea then is, rather than asking for a solution to an equation like this, is to ask for a solution to well, I'll write the problem here in a second, but rather I'm generating a table here of 2 to the x mod 19. Okay, and notice that even though we're talking about 2 to the x mod 19, I only went to 17 because 2 to the 18 mod 19 is 1. Okay, all right. Um, Okay. And so what we're doing is looking at the least positive residue of 2 to the x mod 19. And so here's the list. Okay. Now, what do you notice about this? Well, so 2 squared mod 19 is, or sorry, 2 to the first mod 19 is 2. 2 squared mod 19 is 4. 2 cubed mod 19 is 8. 16 is 2 to the fourth mod 19, of course. So up to x equals 4, this is just the usual 2 to the x behavior. But after that, past this point, it's certainly not increasing because immediately we go back down to 13, then 7, 14, 9, 18, 17, 15, 11. There seems to be no rhyme or reason to this. This seems to be more or less random, randomly thrown in here. So note, once x is greater than 4, this pattern seems to be random. Okay. So some straightforward process for estimating what an x in 2 to the x would be. So given some 2 to the x mod 19, estimating what x is can't be done with some kind of straightforward method like this, of course. So the idea is that when you are considering these logs mod 9, or sorry, these exponential expressions mod 19, looking at tables like this, and of course you can think about doing this for larger and larger primes, you just get a list of more or less random numbers mod that prime. Okay, in this case mod 19. Okay, and so this is what leads to the discrete log problem. So So the discrete log problem, intuitively what I'm asking here is to solve this exponential equation, except I'm doing it mod some prime instead. So given a prime p, a primitive root g, note 2 is a primitive root of 19, right? Because 2 to the 18 is 1. So given a prime p, a primitive root g, and an h that is not congruent to 0 mod p, find x such that g to the x is congruent to h mod p. Okay. So this is called the discrete log problem, abbreviated as DLP. Okay. So box that. This is going to be particularly important for the two applications in Chapter 12 we're going to talk about next. So this is important for the next two crypto applications we discuss. Okay. So, why is it called the discrete log problem? This x is called the discrete log of h, right? So x is called the discrete log of h. All right, and so that's where the name discrete log problem comes from. Okay. All right. So, the question is, what is the importance of this, and why is this important for the next two crypto applications we're going to talk about? So the key point here the discrete log problem is believed to be hard. That is, it is believed to be computationally difficult to solve the discrete log problem. The reason that I use the words believed to be is that this hasn't been proven. Okay, so this hasn't been proved. Okay. So is it possible that there is some very clever way of doing this? The answer is yes, but despite quite a good chunk of time being devoted to discrete log problem or solutions to the discrete log problem, this is something that hasn't been done yet. So it's believed to be hard. And of course, when you have a process like this, it's believed to be hard if if you are smart enough, you can reasonably think that there may be methods to exploit the difficulty of this problem in one direction to use the other direction as part of a crypto system, right? So just like RSA abuses the fact that factoring some large number that's a product of two very large primes is hard, but multiplying them is easy, right? So anyway, discrete log problem is believed to be hard. This is something that you will have an appreciation for if you attempt to actually solve some of these discrete log problems, even for fairly small values. So we will discuss, I'll discuss one of these methods. So we will discuss methods for solving the discrete log problem. Like I said, one I will discuss in detail. The other I will leave to you to read. So one is the baby step, giant step method. And this basically works for P up to like 20 digits. And secondly, we'll discuss what's called the index calculus, which is more or less how this is computed for general P. Works for larger P. But I believe current technology, so current tech can solve DLP up to 230 digit long P. Okay. So I wanted to devote the next little bit to discussing the baby step, giant step method. Okay. And after I'm done, I will give an example of, if we assume P has some size, how much effort it would take to use this method versus trying to brute force check this thing. Okay. So I'm going to go over this one. The index calculus I'll basically leave to you. I'll just mention where you can find the description of this and how this works. Okay. And so what's the baby step, giant step method? Let's see. Do I have enough room here? Might not quite have enough room here, so I might get a fresh sheet of paper. Okay. So here is the baby step, giant step method. And you'll see why it's called that in a second. Apparently this is some other name for Mother May I. Anyway, so what is this method? Well, let G be a primitive root for P. Which of course is prime. Let H not be congruent to 0 mod P. We want to solve the discrete log problem, which is we want to solve the following for x, so g to the x is congruent to h mod p. Okay, so how do we do this? So as I said, if you believe that when x grows even just a little bit, the numbers in that list of g to the x mod p become more or less random, then actually checking the x's would amount to checking tons and tons of values here, right? So this is, so if p is of any decent size, there's a lot of values you'd have to check in the brute force way. So this would be a really, really bad way of going about it. So we clearly want to avoid that. So what do we do here? So here's the process. So first, so let big N be defined to be the ceiling function of the square root of p minus 1. Oh, I put a square bracket there. I didn't mean that. This is the ceiling function. So this is the ceiling function of square root of p minus 1. So this is the nearest integer that is greater than or equal to square root of p minus 1. Right? So it is the smallest integer in with whatever. So, you know, the ceiling of x is smallest integer in with x less than or equal to n. Right? So you round up to an integer if it's not 1. Okay? All right, so that's big N. So once we've computed that, then we make two lists. This is the meat of the process. Okay, the first list is the baby steps, and the second list is the giant steps, or are the giant steps. So this is g to the I mod p, where you let your I go from 0 to big N minus 1. And your second list is h times g to the minus nj mod p for j. So this is for I between 0 and n minus 1. This is for j between 0 and n minus 1. Okay. So we've done something similar to this before, right? In fact, something we did that was kind of sort of similar was when we were doing our one example of how RSA encryption might be broken for small enough encrypted messages. So make two lists, and then I want to look at matches between these two lists. So I want to find a match. We'll get into the question of whether or not we can always do this. Right? In our last process, we couldn't always do this, but here you'll see what happens. So find a match between the two lists. So if you found a match, then g to the I is congruent to h times g to the minus n times j mod p. Okay. But you see what happens here. The second that I have this congruence relation, I can now multiply both sides by g to the n times j to get g to the I plus big N times j is congruent to h mod p. So I've solved the discrete log problem. So writing that in this way, then x, which is I plus big N times j, solves the discrete log problem. Okay. So let's actually do this and see what it is that's going on here. So here's an example. So let's solve 2 to the x is congruent to 9 mod 19. Okay, so take big N to be the ceiling function of the square root of 19 minus 1, which is the square root of 19 minus 1, square root of 18, so next integer above it is 5. Right, and h is 9, and g, of course, is 2. Right? Okay, so the lists are as follows. So let me bring back my process here. So I make two lists, g to the I for I between 0 and big N minus 1, and h times g to the minus nj for j between 0 and big N minus 1. Okay, so let's look at my lists here. This would be big N minus 1, of course, is 4 because big N is 5. So this is 2 to the 0, of course, is congruent to 1 mod 19. So all these congruences are mod 19. 2 to the first is 2. 2 squared, of course, is 4. 2 cubed is 8. And 2 to the fourth is 16. So that was easy. All right, in fact, all those are less than 19, so they're just exactly what they always are. And that's as much as I need to do because I'm going from 0 to big N minus 1. So I'm going from 0 to 4. Okay. Now the next list I do is h times g to the minus big N times j, and j ranges from 0 to 4 as well. So this is 9 times 2 to the minus 0. Well, that's congruent to 9. Okay, and then I have 9 times 2 to the minus 5, so that's 5 times minus 1 here, all right, or minus 5 times 1, whatever. So that's 9 times 2 to the minus 5, so you can compute this is 8. We already have a match, but I'm going to keep going. So 9 times 2 to the minus 10 is congruent to 5. You can think for a second how you would find this, right? So then I would have 9 times 2 to the minus 15. This is congruent to 15. And lastly, I would have 9 times 2 to the minus 20, which is congruent to 7. So I have matches here. There they are. Right? So 2 cubed is congruent to 8, which is congruent to 9 times 2 to the minus 5. Okay? But what this means is that 2 to the 8 is congruent to 9 mod 19. So x equals 8 solves our discrete log problem. Okay. All right. So, question. Will we always find a match? Okay. Well, consider, since g is a primitive root, then there is a solution x with x between 0 and p minus 2. Right. Okay, so write this x in base n, right? i.e., we can express x as a naught plus a sub 1 times big N plus a sub 2 times big N squared, and so on. Right? We can express any integer we want in whatever number base we want. Okay, and of course each of these a sub i's are the digits, right, of x base n. So these are all greater than or equal to 0 and strictly less than big N. Okay, so since big N is defined to be the ceiling function of square root of p minus 1, then big N squared is greater than or equal to p minus 1. But x as a solution is between 0 and p minus 2, so this is definitely bigger than x. Okay. But if I've written x as base n in this way, right? If n squared is bigger than x, then of course this a sub 2 can't be positive, right? So this would give us issues, right? These have to be 0. So all these digits and so on, these are all equal to 0. So x in base n is actually a naught plus a sub 1 times big N, okay, for some a naught a sub 1. But then what do I get? I get that g to the a naught is congruent to g to the x minus a sub 1 times big N, but this is congruent to h times g to the minus a sub 1 big N mod p, right? So this is exactly what tells me I have a match in this case. All right, well that's great. So you know, this this process listing out these things, unlike last time we saw something like this, we get a match, but what's the problem? So the issue is that this is not great for huge primes. So this is fine for primes up to about 20 digits, but for anything bigger than that, we have to use some other method. So to give you, to go back for a second to my description, this algorithm, so these are the baby steps, and these are the giant steps, hence the name. Okay. Now, note if p has 12 decimal digits, then the two lists each have around 10 to the 6 entries. Okay, so only a few million computations are needed. So the reason why this is important to say only a few here is what would this be like if you tried to do this brute force? If p has 12 digits, then doing it the brute force method would require you checking like a trillion p, right? So, but brute force would require checking roughly 1 trillion things. It would require 1 trillion computations here for brute force search. So that's no good. All right, so this is definitely better in this case. All right, but as I said, this works for p up to about 20 digits. So our baby step, giant step method works for p up to roughly 20 or so digits. More than that, and we need to use another method which is the index calculus. So index calculus is more or less like the current state-of-the-art way of looking or of trying to solve the discrete log problem. And as I said, this is computationally currently doable up to p having about 230 digits. So the index calculus, I'm not going to go through it explicitly, but I will say you can find the description of this starting on page 261. On the previous page, there's some preliminary terminology that's cleared up, but so this is done on page 261 if you wanted to take a look at how that goes. Okay, so that's all I want to say about the discrete log problem for now. We're about to see applications of it to crypto systems in a couple minutes, but before we went on, I wanted to especially mention 11.6. So this concerns the existence of primitive roots. So if you remember, one of the big things that we showed when we discussed primitive roots relied on a primitive root existing in the first place. And it turns out they do, and the proof for the existence of these things can be found on page 263 to it finishes by page 266. Okay, so this is the entire content of chapter 11, section 6. So if you want to see how you would go about proving that these primitive roots always exist, then this is how it's done. Okay. So, moving on. So, chapter 12 brings us back to more cryptographic applications, right? So, more crypto applications. And the first thing that we want to talk about in the first section is the Diffie-Helman key exchange. So, as I've mentioned many, many times, I'm sure you're sick of hearing by now, there is the key exchange problem, right? So, the key exchange problem is the following. So, as I said, I can't remember if I've actually used those words yet, but I've discussed this problem over and over again. Suppose you have a way of encrypting that relies on some key, right? But this way of encrypting, once you have the key and once you have the method of encryption down, is 100% secure. It is literally the greatest encryption method, in the universe, right? It's the greatest of all possible encryption methods. The problem is that regardless of how strong your encryption method is, you still need the key to do it, right? And so if you and the person that you want to send encrypted message to are not present in each other's company, if both of you need that key in order to encrypt and decrypt, then you have to send the key somehow, right? But you can't send the key via your perfect encryption system because that perfect encryption system uses the key, right? So you would have to figure out some other way of doing it. This is the key exchange problem. So the point is, if you had a perfectly secure way of sending the key in the first place, there would be no point in your perfect crypto system, since one would already exist because you just used it to send the key, right? And so one solution that we've already seen, we've already seen comes via RSA. right? So the idea being is that you would use RSA to send the encrypted key along, and RSA being a public key crypto system, that makes this easy to do. So the encrypted message you're sending is the key for another crypto system that is your perfect crypto system, or more practically is a crypto system that is symmetric, and so it's faster than doing something purely with RSA or something. So anyway, so this is the idea. So RSA encryption gave you one solution to what's called the key exchange problem, but there's another solution we want to discuss. And that is the Diffie-Helman key exchange. So little note on some terminology here, and I'll mention this again. It's called Diffie-Helman key exchange, but it's really more like Diffie-Helman key definition or Diffie-Helman key establishment system, because you're not really exchanging a key. You're really just using a process to establish the same key. Okay, so one of the neither person in this process, if we're using Alice and Bob as in the previous examples of encryption, neither Alice nor Bob has the key at the beginning of this process, right? So key exchange makes it sound like one of them has the key and they're exchanging it with the other person, right, in a secure way. That's not actually what's happening. So what is going on here is this key is being established by both of them simultaneously. Okay. So that's what's going on here. Okay. So maybe I should write that note. This is more of a key establishment system than an exchange system. Okay. All right. So what is the process? So Diffie-Hellman key exchange is the following. So step 1, Alice and Bob agree on a large prime P and a primitive root G mod P. Okay. Okay. So they agree on this. We'll discuss later here after I've listed this whether it matters if this info is leaked or intercepted or not. Okay. So, second step. Alice chooses a secret integer, A, and then calculates or computes, I like because it's shorter, h sub 1 is congruent to G to the A mod P. Okay. So Alice chooses a secret integer a she doesn't tell anybody about, and then she computes g to the a mod p and calls that h sub 1. Okay. All right. Bob does something similar. So Bob chooses a secret integer b and then calculates h sub 2, by which he means he raises g to the b, computes that mod p. Okay. So the exchange of info hasn't happened yet, right? They've maybe agreed on this large prime p and primitive root g mod p beforehand, or maybe they do this in open channels, right? And again, I'll talk about the implications of whether this needs to be secret or not. So the next step is Alice sends her computed h sub 1 to Bob, and Bob sends his computed h sub 2 to Alice, right? So Alice sends h sub 1 to Bob, and Bob sends h sub 2 to Alice. Okay, so then Alice computes h sub 2 raised to her secret integer. So she computes this k, which is h sub 2 raised to her secret integer a mod p. That gives her something she's calling k. All right, and then Bob computes h sub 1 to his secret integer b mod p, but it turns out that if Bob computes this has to be equal to that same k. Okay. Right. So now Alice and Bob have the same k, the key, with which to do whatever, right? Whatever it is they needed to establish a key for. Okay. So again, you see why this is a key establishment system rather than key exchange, because the key K came from this process. This wording is slightly confusing calling it key exchange because, again, the key didn't exist prior to the beginning of this process. Okay. Okay. So why does this work? If this isn't too, there's not too much going on here in terms of the mystery, but a quick explanation. So how does this work? Well, Alice computed k, which is congruent to h sub 2 to the a, right? But h sub 2 was g to the b, so this is g to the b times a, right, mod p. And Bob computed k, which he did by taking h sub 1 and raising it to the b, which of course is g to the a times b. And we're lucky, we're living in a universe where b times a and a times b are the same. And so we're good here, right? They have the same key. So this key or this K is their shared key that has been established in secret. Okay. All right. So then, note this how of this working is not that interesting because actually, once you pay attention to what this process is doing, this is all that's going on here. So the more interesting question is, why is this secure? Right? So, say eavesdroppers intercept G and G to the A mod P and G to the B mod P. Okay. Well, G to the A, that's H sub 1, and G to the B is H sub 2. So they don't have A and B, these secret integers in this process, right? So the secret integers A and B that Alice and Bob came up with, respectively, they don't have those, but they have G, this primitive root, and they have H sub 1 and H sub 2. That's the thing that Alice is sending to Bob and Bob's sending to Alice, right? So that's what eavesdroppers have intercepted. Okay. Well, then what would they need in order to actually solve this, to figure out what K is? Well, it turns out if they can solve the discrete log problem, then they can use G and G to the A to find A, then raise G to the B to the A to compute G to the AB mod P, which is i.e. K, the key, the thing that this is being used to establish. Okay. But it is unknown whether or not G to the AB mod P can be computed without computing a discrete log. So I think that's important enough to box. That while it is possible, under current knowledge, that there exists a method by which this could be computed without computing a discrete log, one hasn't been found yet. And so right now, the difficulty of finding this key is roughly the same as the difficulty of solving the discrete log problem, which, as I've mentioned, is believed to be a difficult problem. Okay, so this is known as the computational Diffie-Helman problem. So this is the computational Diffie-Helman problem, and this asks for G to the BA mod P given P, G, G to the A mod P, and G to the B mod P. So again, note what things could be intercepted while this process of finding this is difficult, right? It's P, the primitive root G itself, H sub 1, the thing computed by Alice, and H sub 2, the thing computed by Bob. So all those things could be public, and this is still a difficult thing. Okay. All right. So that's Diffie-Helman. There's an example of this that I might say for an office hour if I actually thought I might assign a simple Diffie-Helman problem for homework. Um, so that's how this works. Um, Before I move on to chapter 13, I wanted one more crypto application. So this Diffie-Hellman key exchange can be used in a couple other applications that I'm skipping. So there's maybe I should list them out so that you at least see what it is that's going on. So applications of this stuff. 12.2, this is coin flipping over the telephone. So this is a secure way to have two people flip coins over the telephone and be reasonably sure that they're telling the truth for the result. This is a way of remotely coin flipping without being 100% reliant on the physics involved. And 12.3 is mental poker. It's another application of this sort of stuff. So you can read those if you're interested. Those are really short sections, but it gives an example of what you can do with the ideas behind this key establishment system. So the next thing that I actually want to talk about in detail is the ElGamal public key crypto system. So as I mentioned previously, we've already seen RSA, and the idea behind it was it's a public key crypto system. The reason why the key could be public and everything was fine was that this process of factoring some large integer that's product of two very large primes is hard, right? But multiplying those primes together going forward is easy. And so that's what RSA relied on. So then ElGamal has a similar feel to it, but rather than relying on factoring of large integers being difficult, it relies on the discrete log problem being difficult. Okay, so it is another example of a public key crypto system. And so the difficulty of this is tied to the difficulty of solving discrete log problem. So the difficulty of this is tied to the difficulty of solving the discrete log problem. Okay. All right. So again, assume that we are in a situation where the method of communication I would prefer is one where I can have my key be public. Okay, and I don't need to rely on having a key that no one knows. Okay, so as I've mentioned before, there's various reasons why you might want that. So what is the setup here? So ElGamal setup. So the setup is Alice chooses a prime P and a primitive root G mod P. Okay. And secondly, Alice chooses an X with X between 2 and P minus 2. Of course, it's P minus 2 here because G is a primitive root mod P. So if X were P minus 1, then this thing would be raising g to the p minus 1 would be 1. So Alice chooses an x with x between 2 and p minus 2 and computes h, which is g to the x mod p. Okay, whoop, I'm off screen a little bit. Okay, so then the public information is everything except x, right? So Alice's public info is p, g, and h. Okay, so the prime p that she's chosen, the primitive root g mod p that she's chosen, and this h, which is g to some secret x. Okay, and so the only private info is that x. So Alice's private info is x. Okay. So that's the setup. How does the encryption actually work? So ElGamal encryption is the following. So first, Bob chooses a random number. Y, so whatever Bob likes, with y between 2 and p minus 2, and computes r, which is g to the y mod p. Okay, so then 2, Bob takes whatever his message is, we'll call M, like we always do. So Bob takes his message M and computes C, which is our ciphertext, which is this H to the Y times M mod P. And then he sends R and C to Alice. So he computes R in this way, computes C in this way. So of course, G and P are public info, and H is public info. Right? So the only thing among all of Alice's knowledge that Bob doesn't know is the X that she came up with. So yeah, Bob picks random number Y, computes G to the Y mod P, and then takes his message M and computes H, the publicly available H, to the Y times M mod P. So he gets a pair, R and C. So, and Bob sends R and C to Alice. Okay. So Bob sends a pair RC to Alice. Okay. So then, how does Alice decrypt this? So Alice computes M by taking the C that she was sent and multiplying it by the R that she was sent raised to the minus X, which is her secret info, mod P. And this recovers the M. Okay. Oh, so there's a question in chat that says, how are primitive roots found? So in our discussion of primitive roots, there was there were a couple of propositions that gave us some properties that primitive roots had to satisfy. So the kind of one crude way of doing it was the way that we verified that some given thing was a primitive root for mod. I think 6 mod 41 was an example that we did. So if you are allowed to pick the primitive roots, so if you are the one deciding on the P and the G, then there are you have some flexibility. This is in many ways this can be easier than or I guess less annoying than maybe checking that something is a primitive root, since if you're not dead set on a particular G, you could use one of those properties in the proposition to actually cook up a G from the P given. So maybe actually I'll do an example of that tomorrow's lecture. So maybe at the beginning of tomorrow's lecture I'll do some examples of cooking up a primitive root given some prime. Okay, but that's the answer is those propositions that we covered when we talked about primitive roots are a good source of what has to be true. Once you know those things, cooking one up, like I said, if you're allowed to toy with G and P, then cooking one up is not so bad. Okay, so then the decryption amounts to her taking the C that she was sent, the R that she was sent, exponentiating the R to minus X, which is her X is her private info, and computing that product mod P, and this recovers M. Why does this recover M? So why does this work? First question you always ask whenever you're presented with new encryption decryption methods. So why does this work? So the answer is, note that C times R to the minus X is congruent to, so C is H to the Y times M. All right, so that's H to the Y times M. R is G to the Y. Oh, I'm slightly off camera. So R is G to the Y. So this is G to the Y to the minus X. So then this is, what is this? So this is going to be, so H to the Y, of course, H is, well, let me get my, here, the sheet is cleaner here. So H is G to the X mod P, right? So H is G to the X, so this is being raised to the Y, so that is G to the X Y times M times G to the minus XY. So this is M times G to the 0. So this is just M, right, mod P. Okay. All right. So, note, anyone who knows X, that's all they have to know here, right? So this decryption method, the way that it works is the C and R are being sent along. So anyone who intercepts what Bob sends to Alice intercepts C and R. And so if they know X, they could just immediately decrypt it in the same method that Alice uses. So anyone who knows X can decrypt the message. But if they don't somehow figure out X, right, maybe Alice wrote it on a post-it note in her desk or something. If they don't figure out X in this way, then what would they have to do to find X, right? But finding X means solving the equation G to the X is congruent to H mod P, i.e. solving the discrete log problem. Okay. Okay. So that is directly how, of course, it's related. That's not too mysterious because the way that the setup went, you could tell that the discrete log problem was being involved here, since the discrete log problem going forward is what Alice used to find this X to begin with, right? Okay. And so what's going on here is if Bob's just picking a random Y, then this H to the Y mod P is basically a random number mod P. So at the very beginning of this lecture, I gave you that table of values of 2 to the X mod 19, and you saw that once X was bigger than 4, that those just kind of bounced around. There seemed to be no rhyme or reason. It was just kind of a chaotic list of those numbers mod 19. And so that's essentially the case. So then this H to the Y is basically a random number mod P. So then when Bob forms this C here, he's basically multiplying by a random number mod P, which is what is hiding the message M. Okay. And so, when sending both R and C, of course, he's basically telling her what Y is in a hidden form. But of course, since Alice knows X, she can recover it. Okay, because this line of congruences holds. The one warning I'll give here, so warning is that Bob has to be careful and choose a different Y each time he's doing this, right? So he shouldn't send a bunch of messages successively using the same Y. So warning. Bob should choose a different Y each time. Okay. It's fine if there's some repetitions in, say, a long list, but you definitely shouldn't send a bunch of messages using the same Y. So the reason why is this. So say Bob sends M sub 1 to Alice, okay, using Y, and then Bob sends M sub 2 to Alice using the same Y he used for generating or for sending his message M sub 1. Okay. So Alice receives R C sub 1 and R C sub 2. Why? Well, going back to how the encryption works, if Bob is using the same Y, then regardless of what his message is, this R is the same, right? So if he's using the same Y here, the R he computes those times is going to be the same. Okay. All right. So practically speaking, right, having some repetitions in a long list might be fine, but assuming that everything that could be intercepted is being intercepted, this is an issue, right? So it's an issue when the pair that is sent has, the same R showing up for two pairs Y. So there's no change in this y between messages. So if some eavesdropper can actually figure out one of these messages, say m sub 1. All right, so say that this eavesdropper actually manages to crack this, to solve a discrete log problem involved, and to figure out what m sub 1 is, either through solving discrete log problem or through some other method. Okay, they find maybe Alice copied it down, wrote it again, put it on a post-it note in her desk or something. So if someone is able to figure out what this m sub 1 is, all right, then m sub 2 and any other message using y, any other m sub I using y to encrypt can be deciphered. Why? Well, note that c sub 1 over m sub 1 is congruent to h to the y mod p. And c sub 2 over m sub 2 is also congruent to h to the y mod p. So c sub 1 over m sub 1 is congruent to c sub 2 over m sub 2 mod p. So why is this a problem? Well, now, thus, m sub 2 is congruent to c sub 2 times m sub 1 over c sub 1 mod p. Why is that an issue? Well, I've said that this eavesdropper has intercepted these two pairs and has been able to figure out the first message, m sub 1, through some means. Knowing that, the next message can be decrypted by noticing these congruences, and so since this person knows c sub 1, c sub 2, and m sub 1, they can compute m sub 2 mod p, and that does it. So any successive messages using the same y could be done using the same process. Okay. All right. So that is how this goes. So let's do a quick example of this. So say Bob wants to send Alice the message M, which is 371. Okay, so Alice has already chosen her prime P to be 6,581 and G equals 14, which is a primitive root for P. Again, right, you can think about how you would verify such a thing. So she uses her random number generator. So her RNG is used to pick a secret X, which she has chosen using her RNG with some parameters to be 2,141. So of course, parameters that she could use is X is between, X is between 2 and P minus 2. Okay. All right, so then Alice computes H, which is 14, her chosen G here, to this 2,141 mod 6,581. And it turns out this is 1,543 mod P. Okay, so Alice publishes P, which is 6,581, G, which is 14, and H, which is 1543. Okay, so she publishes this to her online ElGamal public key directory, right? So she keeps X, which is 2,141 private. Okay, so then Bob retrieves her public info and chooses random Y, which is 6,391, and uses this to compute R, which is 14, that public primitive root to the 6,391, and this is 1968 mod 6,581. Okay, and C, which is 371, that's his message, times 1543, which is Alice's published H, to 6,391, right, which is his chosen Y, which is congruent to 6,205 mod 6,581. So Bob sends RC to Alice, right? And so she computes $6,205, just C, times this R, 1968, to the minus X, so that's minus 2,141. And it turns out that this is 371 mod 6,581, which is the recovered M. Okay. So that's exactly how this works. Okay, so those are the last two crypto applications I want to talk about for now. So tomorrow we'll talk about what is probably the high point of the course. It is kind of the one of the more impressive things that comes out of the course, which is quadratic reciprocity. So we will discuss all of the things needed in order to state and understand what it is that's going on there tomorrow when I talk about this. So from here, where we're headed is after we do quadratic reciprocity, I will talk about a couple more practical things. I promised from chapter 14 I would talk about a discussion for primality testing for large primes and how this might be done practically. Apart from that, we are approaching the bit where we are going to kind of sort of be free to more or less explore in this last week of lectures whatever we want in terms of where where to go from here. And so once I finish what is the core curriculum, which basically ends with I'm going to discuss some stuff from chapter 15, and that's more or less going to be the end of the course before we have at least a couple of lectures, maybe like 3 lectures to discuss some interesting things that where this takes us. So I think I may get into elliptic curves was my plan originally, but if you if you have anything that you're interested in that is somewhere on the horizon in terms of number theory stuff, or even not, even if it's something that we've kind of talked about before and you want to hear more about it, then I'm happy to do that. So you can either type comments into lecture, or you can send me emails, or however you want to communicate with me what you want to hear in this last the last week of lectures. So I'll put up an announcement soon that more or less can kind of act like a poll for what you might want to see in the course. But anyway, so that's that, and I'll get into that later. But tomorrow we start on chapter 13. So I will see you all then.